All right, so moving on to number two about neutrino fluxes. Supernova 1987A went off in the Large Magellanic Cloud, or LMC, which is 60 kiloparsecs away. It's this satellite galaxy that's orbiting around the Milky Way, a tiny little galaxy, much in the same way that the moon is a satellite that's orbiting around the Earth. So very local, very nearby. If all of the neutrinos were emitted in the freefall timescale of the stellar core, which we're assuming is about 1 Earth radius, then what was the mean flux of neutrinos at the Earth in units of neutrinos per second per square centimeter? Assume that a 1.4 solar mass neutron star was formed in the implosion. Use the fact that in the formation of a neutron star, every proton gets converted to a neutron via the reaction. Proton plus electron is equal to neutron plus neutrino. So both charge, baryon number, and lepton number are being conserved there. Um, so what I want to do is first talk about the type of flux that we're used to seeing, which is the following in the inverse square law, for example, as the luminosity of a thing divided by 4 pi, the distance the object is away squared. And the way that we're used to thinking of luminosity is as some amount of energy, delta E, that's being expended per unit time, delta T. And I just wanted to do that to do a little bit of dimensional analysis on this type of flux that we are used to dealing with. We'll have units of ergs per second per square centimeter. However, what this problem is looking for is neutrinos per second per centimeter. So I'm going to think of this as a type of counting flux because it doesn't have energy. It has a number in there. So I'm going to define it. So it's supposed to be like a little equal sign with 3 dashes instead of 2. I'm going to define this type of number flux to be number per unit time per 4 pi d squared, because it's not energy flux that's coming through, it's number flux. So again, what I want this to have is units of neutrinos per second per square centimeter, or just per second per square centimeter, since neutrinos is just a count, it's not a real physical unit. Okay, great. So that means we just need to figure out these 3 variables inside this equation, n, delta t, and d. So let's do them in order from easiest to hardest, starting off with d because it's already given to us. 60 kiloparsecs, so we just need to do a unit conversion to it. So we have 60, the kilo in kiloparsecs will turn into a 10 cubed. And then we should just do this problem in CGS because we're specifically being asked for our answer. Final answer to be in CGS units. So we'll need to know how many centimeters there are in a parsec, and that is 3 times 10 to the 18th. And we have nice round whole numbers, so we can actually do this without a calculator to get 1.8 times 10 to the 23 centimeters. Okay, 1/3 of the way done. Now, let's do delta t next. This actually might be the hardest one. None of the 3 of them are terribly hard to find because we are specifically told that the time interval over which this event is occurring is the same as the free fall time scale of that iron core that was happening before the supernova went off. So we're just going to copy our equation for the free fall time scale, which just only depends on constants and then some sort of density. So how I propose that we model this core as a uniform density sphere, so that we can do something with the density that's required for the free fall timescale. So we can just copy over the units right here and do a little mass divided by volume for the density, where the volume of the sphere is 4 pi over 3 r cubed. Don't forget that we're taking the square roots of the whole thing. So in the interest of not writing everything out, just remember that we have an Earth radius for R, 1.4, solar masses for M, and then make sure big G is in units of CGS. And then at the end of the day, we get a really, really short amount of time, barely more than a second, 1.31 seconds. And then lastly, we want to know the number of neutrinos that are emitted in this event. And our favorite way of calculating a big number is to take some sort of large number divided by a small number, or with the large number being the total. In this case, this is the total mass of the star. That's going to be our 1.4 solar masses divided by a mass of the constituent particle. In this case, that is going to be the mass of the neutron, because we're noting that there's a one-to-one correspondence between the number of neutrons and the number of neutrinos. Notice that I'm not using mean molecular weight or anything like that in this problem. And the reason why I'm doing that or not doing that is because there's only one type of particle here. It is neutrons, and usually what lowers the mean molecular weight is the electrons, because they're basically massless compared to atomic nuclei. And the electrons here have all combined with protons to form neutrons in this neutron star. So there's no neutrons here. The only constituent particle is neutrons. So we need to use that. It's basically the same mass as hydrogen or a proton, so nothing crazy going on there. Units of grams will cancel out. And then maybe I'll work to the right here to save some space. You get an absurd number of both neutrons created and also neutrinos released, 1.66 times 10 to the 57th. And yeah, so we have our number of neutrinos, we have our free fall timescale, and then we have the distance that this thing is away. Plug that into this first equation that we kind of derived through dimensional analysis. And then you should get the following number, 3.1 times 10 to the 9th neutrinos per second per square centimeter. So yes, that's the answer. We'll put a box around it. But let's talk about what this means. A second is a very, very short amount of time, and a square centimeter is a really, really small amount of area. And 3.1 times 10 to the 9 is 3.1 billion. So, in the instant, so this supernova went off. It traveled a couple dozen light years to reach Earth. But when it did in 1987, and I was not alive then either, but when it passed through the skin and through the cheeks of the astronomers and the people, when this event happened, literally 3.1 billion neutrinos were passing through each square centimeter of that person's body. So a crazy, crazy number of neutrinos. We don't get core collapse supernovae, type 2 supernovae very often. So this is definitely a rare event and a very local event. So just to let you know about the state of the art of technology at the time, the three best neutrino detecting experiments at the time found a combined 25 neutrinos out of the trillions and gazillions of neutrinos that were emitted, 3.1 billion passing through each person's skin. We only were able to detect 25 of those neutrinos because neutrinos interact very little with other forms of matter. They have a very, very small cross-section, as we say. And one of the fun facts that people like to quote about neutrinos is that they a given neutrino would travel through an entire light year's worth of lead. So if you had a block of or a wall of lead that was 1 light year long, the typical neutrino would be able to 50-50 make it all the way through that 1 light year block of lead without interacting with a single atom that is inside of that lead. So this, both of these examples just show the neutrinos are very, very non-reactive. Okay, and that concludes this problem.